Okay, so let's start talking about section 7.4, in which we're going to be talking about two special sorts of counting techniques, which are permutations and combinations. Okay, and these will have very specific definitions, but before we get to those, let me do sort of some motivating examples. For example, let's look at the following problem. Let's say you're doing, I don't know, a quiz that has 3 problems on it, and you're wondering, well, how many different ways can I go about and complete this? Let's say you do one problem at a time, you complete it, and then you move on to the next problem. Now, typically you'll do the first and the second and the third, but maybe you look through the quiz beforehand and you say, okay, well, I know number 3 right off the bat. Number 1 doesn't seem too hard, and number 2 seems like it's going to take me the most time, so I'm going to do the questions 3, 2, 1. Well, how many different ways can you do it? I can just write them out. So the order of doing the problems, I could do 1, 2, 3. I could do 1, 3, 2. I could do 2, 1, 3. I could do 2, 3, 1. I could do 3, 1, 2. I could do 3, 2, 1. Well, that's a lot of work to write out all the different possibilities to get that this is 6 possibilities. But we've already seen the multiplication principle gives us a better way of doing this. If I let O1, so this is 6 total possibilities. If O1 is the first problem I do, and O2 is the second, and O3 is my third, these are my operations, then I've got 3 choices. The first problem I do, the second problem I've already done once, so the second one has 2 choices. And what's the third problem I do? Well, if I finish the first 2, I've got 1 left. So the total number of ways of completing the test is 3 times 2 times 1 is 6. Okay. Similarly, we already saw the example of locker combinations, and we saw that the total number of ways of having 3 numbers from the numbers 1 through 40 was 40 times 39 times 38. Here we're assuming no repeats. And this was some number. I don't have it pre-computed, so you could just refer back to one of the previous lectures to see what that is. But my point here is that look at these sorts of products here. I've got 3 times 2 times 1. I've got 40 times 39 times 38. We keep seeing this sort of multiplying a number and then the previous number and the previous number. So this actually motivates a definition of something called a factorial. That does not look like an A. Something called a factorial. So what is a factorial? Well, the factorial is going to be for any number n, which is greater than or equal to 0. Well, we first define 0 factorial to be 1, and then n factorial for any number which is bigger than 0 will be n times n minus 1 times all the way down to 2 times 1. It's really the product of the numbers between 1 and n. Okay. So let's just look at a couple of examples of these, and as you can imagine, these get harder to compute when you have to multiply a lot of numbers together. So for example, 1 factorial, well, it's the product of the numbers between 1 and 1, so it's just 1. 2 factorial is the product of the numbers between 2 and 1, that's just 2 and 1, so it's 2. 3 factorial is 3 times 2 times 1, we already saw that. So that's 6. 4 factorial is 4 times 3 times 2 times 1. 4 times 3 is 12, times 2 is 24, times 1 is still 24. Let's just do one more. 5 factorial is 5 times 4 times 3 times 2 times 1. 5 times 4 is 20. That's 20. Times 3 gives me 60, and times 2 gives me 120. So the total there is 120. Great. Those are just the first couple of factorials. Notice that they grow pretty big. But let's note something. Each factorial, say 3 factorial, was 3 times the previous guy. It was 3 times, this is 2 factorial. 4 factorial was 4 times 3 times 2 times 1. It was 4 times 3 factorial. 5 factorial was 5 times 4 times 3 times 2 times 1. That's 4 factorial. So 5 factorial is 5 times 4 factorial. Okay. This actually gives us a nice sort of formula or a general rule for computing factorials. I can compute n factorial by taking n and multiplying it against the previous factorial. And let's note here that when I write n minus 1 factorial, this means take the factorial of whatever n minus 1 is. If n is 5, plug in 5 here, and you get 4. This is not n factorial minus 1. Okay. But let's do a couple of examples of using this fact. So, for example, what is 6 factorial? Well, this is 6 times 6 minus 1 factorial. That's 5 factorial. And 5 factorial we already saw was 120. So that means that 6 factorial is 6 times 120, which is 720. What is 7 factorial? It's 7 times 6 factorial. So it's 7 times 720, which is equal to, I did this before, 5040. Great. So that's another way of computing factorials. If you know a factorial, you can get the next one by multiplying out. But this also helps us out when we're looking at sort of quotients of factorials. So for example, let's compute the following quotient of factorials. Let's do 100 factorial divided by 98 factorial. Well, 100 factorial is 100 times 99 factorial. Okay, divided by 98 factorial. And I'm going to pull apart 99 factorial to 100 times 99 times 98 factorial. So 99 factorial is the same thing as 99 times 98 factorial, and I'm still dividing that by 98 factorial. Why did I do this? Now I've got a factor of 98 factorial on top and on bottom. I can cancel those guys out, and I'm left with 100 times 99, which is 9,900. Okay, that makes things a little easier for us. So note what I eventually got there. 100 was equal to 100 factorial was 100 times 99 times 98 factorial. In fact, that's generally true. If I want to reduce a factorial to a previous factorial, I can keep writing out the numbers less than what I'm starting with, and then stop at some point and put the factorial on that. So 100 factorial is equal to all of these different products. You know, let's suppose I, for some reason, wanted to get down to 93 factorial. I could say 100 factorial is 100 times 98 times 97 times 96 times 95 times 94 times 93 factorial. All I'm doing is using that previous rule over and over again, but the basic deal is I write out all the numbers between 100 and 93, and then I put the factorial on 93. So generally you can just write out all the numbers, starting from whatever you wanted to start at, going down until you get to the number that you want to be there and put a factorial. Why do I want to do this sort of thing? Well, let's compute one more guy. Let's do something that looks like this. Let's compute. We're going to be seeing things eventually that look kind of like this. 10 factorial over 6 factorial times 4 factorial. Now, again, whenever I have factorials, I can get nice cancellation. And the way that I'm going to get it, well, I know that I can write 10 factorial out until I get to, say, 6. And then I'll have a 6 factorial on top to cancel with the 6 factorial on the bottom. So I get 10 times 9 times 8 times 7 times 6. I'll stay with the 6 factorial. Why don't I go down to 4 factorial? Because 6 factorial happens first, so it'll be, it's less for me to write down. So I can cancel out the 6 factorials, and I'm left with 10 times 9 times 8 times 7. Now let me also write out what 4 factorial literally means. It's 4 times 3 times 2 times 1. Okay. There's not going to be nice cancellation like we had up here, but it turns out whenever we have something that looks kind of like this, where these two numbers on the bottom add up to the guy on top, we will have cancellation. And it goes like this. You kind of have to just do it depending on the situation. 4 times 2 gives me 8, so I can cancel 8 out with 4 and 2. 9 and 3, well, I can cancel a 3 out and get a 1, and a 3 out upstairs and I get a 3. So I'm left with 10 times 3 times 7 on top. On the bottom I have 1, which leaves me with 10 times 3 is 30, times 7 is 210, over 1, which is just 210. Okay, so that would be my final answer here. So, yeah, I'll put a lot of examples like this. I'll do them in class, and we'll see it in homework.